Hello, students. From the moment we wake up and switch on a light to charging our phones at night, electricity is a part of almost everything we do. It's this amazing, invisible force that powers our daily lives.
But have you ever stopped to think about what is actually happening inside those wires? What is this electricity that's flowing through them to make our bulbs glow and our fans spin? Well, that is the main question we are going to explore together in this lesson.
So, here's our plan for today. We will start with the basics. Then we'll try to understand what electric current is and the push that makes it flow, which is called potential difference. After that, we will learn how to measure them, solve a few problems, and then we will summarize everything.
We all know that electricity is a very convenient and controllable form of energy, but to truly understand it, we must start from the very beginning, with the most basic idea.
And that beginning is something called electric charge. You can think of electric charge as the fundamental stuff of electricity. In metal wires, like the copper wires we use, this charge is carried by very, very tiny particles called electrons.
So we have these electrons which carry charge. But what happens when these charges start to move? Well, that brings us to our next very important topic, electric current.
Electric current is simply the rate of flow of electric charge. Let me give you a simple analogy. Think of a river. The flowing water in the river is called a water current, right? In the exact same way, the flow of electric charge through a conductor, like a wire, is called an electric current.
Now, this is a very important point, so please listen carefully. We now know that it's the negatively charged electrons that actually move in a wire. And since they are negative, they flow from the negative terminal of a battery to the positive terminal. However, when electricity was first discovered, scientists did not know about electrons. They made a guess that positive charges were flowing, from the positive to the negative terminal. This historical idea is called conventional current, and even though we know it's not what actually happens, we still use this conventional direction in all our circuit diagrams today. So, just remember this.
Now, for this current to flow, it needs a proper path. This path must be continuous and closed, like an unbroken loop. We call this complete path an electric circuit. If there is a break anywhere, the current stops flowing. Just imagine a simple torch. The switch in the torch has a very simple job. It either completes the path or it breaks the path. When the switch is open, there is a gap, so the path is broken. No current can flow, and the bulb does not glow. The moment you close the switch, the path becomes continuous. The current starts to flow, and the bulb lights.
We can express this idea mathematically with a simple formula. We say I equals Q divided by T. Here, I is the symbol for electric current, Q is the net amount of charge that flows past any point in the circuit, and T is the time it takes for that charge to flow. So, current is simply the amount of charge flowing per unit of time.
Now let's talk about the units. The SI unit of electric charge is the coulomb, and we write it with a capital C. The unit for electric current is the ampere, written with a capital A. It's named in honor of the French scientist André-Marie Ampère. So what is 1 ampere? 1 ampere is simply the flow of 1 coulomb of charge in 1 second.
To give you a better idea, 1 coulomb is actually a very large amount of charge. It is equal to the charge contained in about 6 × 10 to the power 18 electrons. That's a 6 with 18 zeros after it. It is a massive number of electrons.
All right, so we know that current is the flow of charge. But what makes the charges move in the first place? Why do they flow at all? Let's find out.
Let's go back to our water analogy. Imagine you have a tube filled with water, and it's lying perfectly flat on a table. Will the water flow? No, of course not. It needs some kind of push, or a difference in level. The same thing is true for charges in a wire.
You see, for water to flow, we need a pressure difference. For example, if we connect one end of the pipe to a tank placed at a higher level, the water will flow down. Similarly, for electric charges to flow, we need a difference in what we can call electric pressure. This push or electric pressure difference is provided by a cell or a battery, and it has a proper name. We call it potential difference.
So, we define potential difference, which we represent with the letter V, as the work done, W, to move a unit charge, Q, from one point to another in a circuit. And what does this work? The chemical energy stored inside a battery or a cell does the work of pushing the charges around.
The SI unit for this potential difference is the volt, represented by V, and it's named after the Italian physicist Alessandro Volta. The definition is quite simple. A potential difference of 1 volt between 2 points means that 1 joule of work is done to move 1 coulomb of charge from one point to the other.
Okay, so we've understood the concepts of current and potential difference. But in a real lab, how do we measure these quantities? Let's look at the special instruments we use.
We use two main devices. An ammeter measures current, and a voltmeter measures potential difference. Now, it is very, very important to understand how they are connected. An ammeter is always connected in series. That means you place it right in the path of the current so that the entire current flows through the ammeter. A voltmeter, on the other hand, is always connected in parallel. It measures the potential difference between 2 points, so you have to connect it across those 2 points.
You know, the best way to really strengthen our understanding of these formulas is to apply them. So let's solve a couple of numerical problems together.
Here's our first problem. A current of 0.5 amperes is drawn by a bulb for 10 minutes. We need to find the total amount of electric charge that is flowed through the circuit.
Okay, let's solve this step by step. First, we always write down what is given. So current, I, is 0.5 amps, and time, T, is 10 minutes. Now, be very careful here. The SI unit for time is seconds, so we must convert minutes to seconds. 10 minutes is 10 multiplied by 60, which gives us 600 seconds. We need to find the charge, Q. We know the formula is I equals Q over T. If we rearrange it to find Q, we get Q equals I multiplied by T. Now we just put in the values. Q equals 0.5 amps times 600 seconds, and that gives us our answer, 300 coulombs.
Very good. Let's try one more problem, this time involving potential difference. The question is, how much work is done in moving a charge of 2 coulombs across 2 points having a potential difference of 12 volts? Let's use the same method. First, what is given to us? The charge, Q, is 2C, and the potential difference, V, is 12V. We have to find the work done, W. The formula connecting these is V equals W over Q. To find W, we rearrange the formula to get W equals V multiplied by Q. Now let's substitute the values. W equals 12V times 2C. That gives us a final answer of 24, and the unit for work is joules, so 24J. We have covered quite a few new ideas today, so let's just take a moment to calmly summarize the complete story of what we have learned.
So let's connect all the dots. Everything begins with electric charge. When this charge flows, we call that flow electric current. But what makes the charge flow? A cell or a battery does work, using its energy, to create a push. This push is the potential difference, and it is this potential difference that makes the current flow around a complete circuit.
And this leads us to a final, very interesting question to think about. Is this flow of charge always smooth and easy? Or is there something inside the wire itself that tries to oppose this flow? That something is called resistance, and we will explore that very important concept in our next lesson.